Good morning, Astronomy 1010. This is our 5th week of lecture. We're going to learn a little bit more about Newton's laws today and kind of make our transition into discussing atoms and light, which will start probably on Wednesday. Something to be aware of while I've got your attention, next week is the exam. Is that correct? Someone want to back me up on that? If we go to our syllabus, 1010 schedule, let me tell you the way I did this last semester and a slight difference that I'm going to do this semester. So midterm exam is Monday, March 1st, and I'm just going to confirm, yes. So our exam is 1 week from today. That's something we need to think about. Obviously, that's going to be a point of stress for several of you, probably for everyone. Exams are stressful. There are things that I'm going to try to do to make it better. One, on Wednesday, instead of a typical homework, we're going to be doing practice problems for the exam. So that means we're going to have a homework session just like any other, except this time, instead of doing questions from the book, we're going to do questions that I've made up that are similar to the exam's questions, just as a way to kind of prepare ourselves for what it's going to be like and practice solving those problems on our own before we have to do it real time. Does that sound like a good idea to everyone? Yeah. Now, Austin was here from my previous class. Austin, did you feel like those practice problems were helpful for the exam? I don't know if you did them or what, but.
Yeah, I did. They definitely help a lot. Just kind of like going over.
That's a worthwhile thing for us to do.
Yeah, like going over like the math and the context of everything, like of what we're going to see helps a lot, I think.
Yeah, I mean, I was thinking if I were you guys and I was a student, when I remember taking these really crazy physics exams, so much of the anxiety was I just had no idea what they were going to ask me. And I couldn't even try to imagine what the questions would be like until I was doing them. And then there was like time pressure, and that was extremely stressful. Now, you guys are going to have a bit more time than I used to, because I would have, 60 minutes, pencils down, that's it. We're not going to do it like that. We're going to give you oodles of time. In fact, here's where I think it's going to be different. Last semester, the technique that I tried was I thought, let's just pretend this is like a normal class and we'll have exam during the class time, even though obviously not everyone can be here for the live session. But I kind of left the exam open for the whole day. And then I tried to be around and available to field questions if you had them. Another thing I did was I actually tried to log in live, and everyone kind of logged in live and muted their cameras. It didn't work on so many levels. One, I kind of ended up being kind of glued to the computer, but doing nothing for vast majority of the time. And the other issue was only a few of you actually show up to the live session. We've got 14 people here, only 4 of whom are sharing video with me, maybe 5 if Zachary comes back. So there were so many others who are going to be watching this recording later. I've also started to realize that a lot of you guys can sometimes play catch up on the weekends because you might have some work stuff going on during the week. Maybe I think what I'm going to do this year, and you guys can give me some feedback and tell me what you think. I'm just going to leave your exam open from Monday all the way to Tuesday. And everyone in my class can just kind of take it anywhere in that block that works for them. I won't be logging in live because that's just a huge window of time, but I will be available and doctor on call. And if you get into a pickle or you have a question, which you will eventually, you could either text me or call me. You could also email me, but since I'll have my phone in my hand, texting or calling might be faster if that's something you're comfortable with. How do you guys feel about that? Does that sound like the good way to do things for you? Or at least you can't think of anything better, right? I can't.
Could always just give us the answers.
Well, in a way, John, I kind of am, because I'm going to be doing practice problems with you. It won't be the exact answers of like fill in C on question 27, but it's as close as I can get to giving you the answers without giving you the answers, which would just be stupid, right? There's kind of no point to the test.
It is multiple choice.
It will be multiple choice, but it's going to be tricky because it's going to be very similar to the homework where there's different sections, and I'm going to go over this on Wednesday, so I shouldn't repeat myself, or maybe I should, because people tend to not listen to me. There'll be a section with diagrams where you have to pick the correct vocabulary term. There's a section with general questions, which could just be like a conceptual thing, like suppose the distance to the moon were twice as far away. Could I still have a total solar eclipse? And then there will be math questions, which are like the homework, with a setup with givens and multiple parts where you have to do some math problems and some unit conversions. So even though it's multiple choice, a good part of the test will feel a lot like doing the homework, broken down into multiple choice bits. In other words, just because it's multiple choice does not mean it won't be stressful. You'll be given a formula sheet with all the conversion factors you need. Obviously, you'll be taking it at home, so it's open book, open internet. Cheat if you can cheat, okay? Because I can't police you, nor do I have any interest in being your policeman. I think the test, even if you are cheating, will be plenty challenging enough. And it will take a long time because there's 100 questions. That's a slog. Jenna. Jenna,
Sorry.
you're muted. Oh, yeah.
Oh, sorry. You kind of just answered it. Do we have a time limit?
No, I decided, so some people have disabilities waivers to sign because they need a little bit more time. I was always a really slow worker. I was the guy who like took 3 times as long to do everything. So I'm a little sensitive to that. So I figured if I just leave it open, you can't like close it and come back to it. I think once you open it, you have to kind of keep working on it. And I suppose you could kind of keep your laptop open and go get a snack if you need to power up or carb up or whatever. But in general, there won't be so much of a time limit, except I'll open it on Sunday and I'll close it on Tuesday at midnight. And that's it. I mean, you can't do it in 3 days. What the F, right? Does that sound reasonable? And if anyone does have some problem, like someone unfortunately was in a car crash this weekend from our class, and I need to talk to him. I hope he's okay. So obviously I can make special accommodations if there's something really crazy going on in your life. But otherwise, I'd expect 3 days to be a good enough window between Sunday, Monday, or Tuesday. All right. I mean, if anyone's got other thoughts, then this is a good time to let me know. All right. Enough administration. Let's get down to talking about science. Unless there are any other questions, we're going to return to our subject of Newton's version of Kepler's third laws.
So I have a question. How many days do we have to do the exam?
Well, you'd have 3 days.
Okay.
Right? Sunday, Monday, Tuesday.
Okay.
And you just have to do it sometime in there. I suppose you could start it Sunday morning and you could stretch it all the way to Tuesday if that sounds like fun to you. I personally would rather get it done in an efficient way. But since it is a long test, since it's 100 questions, I could see needing to take a break in the middle and, you know, eat a bowl of pasta or something to get your energy back up. Does that sound acceptable to you, Yudi? I'll just assume that the answer to that is yes.
Yeah, sorry, yeah.
Okay, all right.
Thank you.
Okay, everyone, if you guys want to play and interact with me, let's talk a little bit about what we learned last time. And this is stuff that, of course, is going to be on the test. So we will remember that Sir Isaac Newton gave us 2 different concepts that we learned about last time. Now, I opened a fresh marker. Where? That's not it. That's not it. That's not it. That's not so bad. We had his laws of motion. And then we had the law of gravitation. I'm sorry, students, I need to turn the heat down because I am literally sweating buckets. 1 second. All right. Sorry about that. Do you guys remember what Newton's second law of motion was? Okay, someone needs to interact with me today, or I'm going to hang up and give you the pre-recorded video.
Which one? The
second of his
an
laws
object
of
at rest
motion.
stays at rest unless
That's the law of inertia. That's his first law of motion.
Is it that F equals force equals mass times acceleration?
Yeah. I would say of his 3 laws of motion, the second law is the most important, or at least that's the equation I was tortured with the most in my entry-level mechanics courses. This is a surprisingly complex and useful formula. It tells you how things move when you push them. That could be interesting. He also has a law of gravitation. Big G times mass 1 times mass 2 over the distance squared. This tells you about a particular force, a force of nature, gravity. They're separate concepts, but you can combine them and synthesize them to learn and discover new things. Last time I told you that these 2 laws were used together to derive something called Newton's version of Kepler's third law. That's a big topic in this class. It's also the subject of today's lab. We're going to be calculating the period of a space shuttle. Today's lab is kind of like a math exercise. Also, great training for the exam because I'm going to be asking you questions just like the one in today's lab. So you can think of even today's lab as a sort of pre-game for the exam. Unfortunately, showing you the exact details of how you can combine these 2 to derive Newton's version of Kepler's third law is a little bit mathematically complex. It involves calculus, and it takes a couple of class periods to do it, which we don't have. But I can show you another simple example that'll give you the flavor of the feeling, and I think we might learn something by doing it. So let's try a little example. This is going to be, how could I combine these 2 equations to learn something new or newish about my universe? So let's consider a problem that might have been interesting to Isaac Newton, and that's the problem of an apple falling from a tree down to the surface of Earth. And of course, the joke here is that Newton was supposedly inspired by the fall of an apple. So we're going to take our little apple here, and it's going to fall off of a branch and fall down to the surface of Earth. I'm going to draw in the radius of Earth because that's going to factor into today's problem. You guys will notice that I used a circle with a cross. That is the symbol for Earth in astronomy, in astrology, whatever. The Earth has a mass. The apple's mass, I'm going to use a lowercase m for because it's so much smaller than the Earth. And we're going to probably want to consider the height of a typical apple tree. So I don't know if you guys are comfortable thinking in meters. If we have any European friends here, maybe so. How tall is a typical human being? How many meters tall?
2.
Good. So what would you say, Jenna, about an apple tree? Have you ever gone apple picking before?
Yeah, probably like 3 meters tall.
Yeah, they're not as tall as a pine tree, right?
Yeah.
3, maybe 4. Crazy, if we're talking a tall apple tree. So let's go with Jenna's estimate of 3 meters. I think that's totally reasonable. I'd say the height of my room is probably about 3 meters. So that seems to me about apple tree height. And let me really explicitly state the question we are going to try to answer. We're going to try to use these 2 equations to answer the following question. What acceleration will the apple feel as it falls to Earth? This is the sort of question, a simple version of how we could combine both of these equations to learn a truth about the apple's fall in the gravitational field of Earth. Okay, so I don't know if you guys can take a guess what we're going to do here, but we're going to take this equation to describe the gravity between the apple and Earth, and we're going to use this equation to describe the apple's motion, okay? So let's first start with the F equals ma part. The apple will experience a force which will cause the apple to accelerate. And here we're going to consider the mass of the apple because that's what we're interested in calculating, the acceleration of the apple. Now, I'd like to say that if we were particularly perverse, we could use this formula to consider the acceleration of Earth due to the apple. Technically speaking, both objects feel a mutual attraction, and Earth will, in some crazy way, feel a slight gravitational pull towards the apple. Of course, the Earth is so much more massive than the apple that the Earth effectively will not move. It's basically fixed, and it's the apple that will undergo the acceleration. However, when the two objects are less mismatched, it would be a kind of mutual attraction, and it might be more interesting to ask that question. Here, we're going to practically assume that the Earth is fixed, and it's just the apple that experiences an acceleration. So we will write the force on the apple is, and I'm going to use red for the mass of the apple times the acceleration. And of course, it's the acceleration that we're interested in calculating. Here's where we can use Newton's second equation. We know that this force isn't a random force. This isn't leprechauns forcing the apple to the Earth or some kind of other magic. This is gravity, which is pulling the apple to Earth. So this force is caused by gravity, and we can set this force equal to Newton's law of gravitation. Here we have big G. We have the mass of Earth times the mass of the apple. And here what we need to do is consider the distance between them. Usually the distance is the center to center distance between the two objects. Here it might be nice to remind everyone that the radius of Earth is 6,400 kilometers. And the mass of Earth, 6 times 10 to the 24 kilograms. I would estimate the mass of the apple to be about 300 grams or so. That's 0.3 kilograms. It's probably not going to matter because we're not going to actually need this, as you'll see in just a moment. But a typical apple mass is 300 grams. So Jenna, since you were kind enough to interact with me and tell me the height of an apple tree, what do you think we should use for D here, the center to center distance?
Center to center distance would be the 6,400 kilometers minus 3 meters.
Wait,
The
why
diff-
minus? Minus?
Oh, it would be added.
Okay, yes, it would definitely be added. It wouldn't be minus, right? Because, well, you know, if you're going from center to center, right, you have to add all those three together, not subtract.
Yeah.
Okay, so are you worried about adding kilometers and meters? Because I am.
Yeah, we should convert the kilometers to meters.
All right, so since you're going to have to do this on your own in the test, do you want to demonstrate your excellent powers of dimensional analysis for me? I'm actually going to do this up here, if you don't mind. I want to keep the bottom for something else. So let's, geez, I hate to make this all messy. I wish I could scroll this up. You know what? I'm going to do it down here after all. Okay, so tell me what to do. Tell me how to convert that to meters.
Okay, so we write down the number to convert.
With its units, right?
Yeah.
Don't leave me hanging here. So let's pretend that my hand is your hand. Tell me what to write.
Okay, 6,400 kilometers. And you write the multiply times the division bar. And then on the bottom, we write in our units of kilometers, and on top, meters. And then the conversion factor is 1 on top. Or is it 1,000? Yep. And
Well,
1,000. I'm pretty sure it's 1 on top and 1,000 on the bottom.
Okay. And now we punch it up.
Yep. And we get 6.4 meters.
So the radius of Earth is 6 meters.
No. I did it backwards.
See
Oh,
how long I could get away with this.
oh goodness, I'm sorry for wasting the time. Okay, so it's
No,
backwards.
hold on, Jenna. Let's just stop. You did not waste time. Do you know how many people out there are going to be doing this on the test? A lot of people. I've seen it so many times. This was the most useful thing you might have done today, is show people to not do this mistake and to learn it yourself. Why is this wrong? What did you do wrong?
I had the ratio wrong, or the proportions.
Right.
different.
And let's talk about the formula sheet. Okay. So let me see if I can find this for you guys quick, because this is going to be another question that's of interest to people. Just a second here. My taskbar is always in the freaking way. All right, let's go to my equation sheets. Hold on, bear with me, guys. I'm doing a thing here. And you guys are astronomy 1010, and this is the midterm formula sheet. So let me give you a sneak peek of what your formula sheet's going to look like. In fact, if you guys want, we can start practicing with it today. Share screen. Can you guys see my screen?
Yes.
All right, thank
Yeah.
you.
Yep.
This is what your formula sheet's going to look like. Of course, since it's open notebook, you have all the formulas scattered throughout your notebook, but I've noticed you guys sometimes take a while to find things. In addition to having formulas, we also have a number of useful conversions, including the one that you were just working on. Not only did you get the ratio wrong, but I would think of it like this, Jenna. You made a failure to keep the number next to its appropriate unit. 1 goes with kilometer, 1,000 goes with meter. Do you see what I mean? Even if this is written down, this can still be difficult. That mistake can be made. I've just seen it, okay? In fact, would you guys like me to email this to you, the entire class right now, so that you can start practicing with it? That sounds like a pretty good idea,
Yes,
right?
please.
Hold on, how do I do this? Share screen. Here's the internet. Here's Blackboard. Email all users. Hopefully this is the same group. So this is AS1010 midterm formula sheet. There's a different one for the final. I'm just going to say this is the formula sheet. Hopefully people who are watching this later, they're going to get the email now, but they'll remember that you all have this email is the point, okay? CCRI exams 1010 AS1010 formula sheet. Submit. Good. So why don't you should get that instantaneously, I hope. Boom. Okay. So you guys can all open that up, and I would actually either print it out or have it on your iPad or whatever, so you can use this as we go. All right, back to the action. What do I do, Jenna? Fix it for me.
All right, so you write 1,000 on top, 1,000 meters to 1 kilometer.
Okay. And then what do you get?
And then you punch it in, you get 6,400,000.
Put it in scientific notation.
Oh yeah, 6.4 times 10 to the 6th.
That's right. And Jenna, you could have even done this without a calculator. You know how I would have done it? I would have looked at this and I would have said 6.4 times 10 to the 1, 2, 3, 4, 5, 6. You can even just see it, right? Okay,
Yeah.
now remember what we were talking about 10 minutes ago. Jenna suggests that we should add the radius of Earth plus the height of the apple tree. So go ahead and do that. And what do you get?
.4.
6.4.
Well, you would, if you kept it in the scientific notation, because if not, it'd be what in meters, 6,400,003.
Right. So I'm trying to make a point here. I just don't understand if anyone gets it. What's my point?
The mass of the apple is in
Not
regard.
radius of.
Well, the radius of the apple is nothing in comparison to the Earth.
Yeah, the height. It's actually it's not even the radius. Well, the radius of the apple in theory should be figured in as well, but that's even less. The height of the apple tree doesn't matter because 3 meters is nothing compared to 6,400. Basically, the distance between them squared is just the radius of Earth squared. The height of the apple tree, unless it was as tall as a space station or something, doesn't matter. So let's remember, okay, actually, what are we trying to do? What's our objective? I just want to make sure you guys didn't get lost in the sauce here. You're totally lost in the sauce, right? What are we doing?
We're looking for the acceleration of the apple.
Thank God. Okay. And notice, if we want this, we're going to have to clean this equation up. Ooh, I see something useful about to happen. It looks like the mass of the apple appears on both sides of the equation. Jumping Jesus, we can cancel those two things out. And now I have an expression for the acceleration of the apple. I'm going to have to take it upstairs here because I'm running out of board space and I'm getting squished. Okay. So the
I
formula
think
that
you
we
need to
have
get a
come
bigger
up with,
whiteboard for Christmas.
say that again. I need a bigger whiteboard, right?
Bigger-
Unfortunately, my
bigger-
camera's only so big.
Bigger whiteboard for Christmas.
I know they're expensive, you know. The smartest thing I ever did was to borrow this from the basement of CCI about a year ago. Before I was clairvoyant, I knew I would need this one day. Okay.
What about building a board and then doing like a chalkboard paint?
I love using chalk, although it gets a little dusty in here. If you want to help me get a chalkboard, sure. I don't know if I've got those ambitions or skills, but if you guys have some, then I'd be all too appreciative. You can make me a nice Christmas present. Okay, the expression we have for the acceleration of the apple is this equation, big G times the mass of Earth divided by the radius of Earth squared. Do you guys think we should calculate this? I think that might be a groovy idea. So the acceleration would be big G, 7 times 10 to the minus 11. The units, of course, are meters cubed per kilogram per second squared, times the mass of the Earth, 6 times 10 to the 24 kilograms in MKS units, divided by 6.4 million meters square thereof. Why don't you guys try to punch that into your calculator as your first of many warm-up calculations today? And I will get some iced tea while you slowpokes punch it in. Okay, what do we got? Time is money here.
Um, 4.1 to the 13th times 10 to the 13th.
Jenna, you did the same thing I think you were doing last class. When you hit the square, it
Yes.
squared this and you thought you were done.
I know. I got a different answer. It's 10.3 times
Let's not mess around with 0.3s. Life's too short for 0.3s, Jenna.
0.25.
Round it harder.
10.
10. You've got one sig fig at best anyways. 10 what? I don't understand 10. I need units.
MA. Oh, wait, no, sorry. Hold on.
Oh my God, you guys know what M stands for, right? You know what KG means. You know what S means, I hope. Ryan chimes in with the correct answer of meters per second squared. Let's see how he got that. Meters squared, the square distributes to the meters, cancels with 3 meters, leaving 1 meter behind. Kilogram cancels top and bottom upstairs, and you're left over with 1 meter per second squared. which of course are units of acceleration. Is this a random number?
It's the little g formula.
That's right. This isn't any old acceleration. This is something we've seen before. It's little g. Who discovered little g? Did Newton discover little g?
Galileo.
Yeah. So Jenna, what was the purpose of all this? Newton analyzed the fall of an apple, and he discovered the same answer that Galileo discovered 100 years before he was born. Was this a waste of time? Or is there some purpose to this exercise? What good is it to do all this math and come up with an answer that how did Galileo come up with this? Did Galileo do the math? Who remembers the history of astronomy lesson? A week ago, you learned about how Galileo did this. I thought it was a compelling story. Maybe you didn't. No one?
I guess that he built
This
the
is
first.
why oh, sorry. Go ahead.
Sorry.
I'm just
No, I was just saying the observations of Galileo.
It wasn't part of the telescope observations. This was one of his physics experiments. He did a million other cool things that I didn't have time to tell you about, but I did tell you about this one.
Is this the experiment he did with that ramp?
That's right. Thank you,
that ball?
Paul. Thank you for helping there. Don't you guys remember? I thought maybe I'm just a physics nerd, and so that's why I think all of this is interesting. But I thought I showed you guys. Do I have it here? Where do I have this thing? Oh, damn it. It's in the history section. Hell, I can just call it up on the internet. If I were to type Galileo ramp, the thing exists somewhere in the Museum of Galileo, like this thing. They call it the inclined plane. Do you guys remember this picture? I thought this was an impressive artificer, as Newton would call it. It's an impressive artificer. Artificers are what Newton says you can use machines to experiment on nature. Galileo discovered 10 meters per second squared by rolling spheres of different densities down this ramp and timing it by them tinkling bells and him listening to the tinkling with his ear. This is a totally different method of discovering little g than what Newton has just done. Remember that Newton derived this by combining his law of motion with the law of gravity, and he rediscovered a truth that had already been known. My question to the class is, can you think of why this would be useful for some reason? Because to me, this still seems useful, but I'm wondering if you guys can see what advantage we have here. Galileo did not know about the force of gravity. He didn't know about big G. He didn't know what the mass of Earth was. He did know what the radius of Earth was because Eratosthenes figured it out thousands of years ago with sticks. That was clever of him. But besides that, Galileo could not have done any of this. And remember that little g only holds for Earth. After all, this is called the local gravitational acceleration of Earth. If you went to the moon, if you went to Mars, little g would not be the same. The g forces on that helicopter flying around in the Perseverance mission are not 10 meters per second squared. There's less gravity on Mars because it's a smaller and more importantly, a less massive planet. This is a story about the two different types of physicists that we find in nature. And each of them has an important contribution to make to science. In the first case, you have someone like Newton. Well, let's take Galileo for starters. Galileo is a type of physicist that we would call an experimentalist. That's how they refer to them in physics. And Newton is a different type of scientist. He is what we would call a theorist. And these are two different methods of using science to investigate nature. In the case of Galileo, the experimentalist is kind of like a Super Mario Brothers type of scientist. They're a grease monkey with the overalls and the wrench, and they get out there and they polish an inclined plane and they carve out some spheres, and they actually roll the sphere down the ramp, and then they measure the tinkling of the bells, and that's how they discover that all objects fall to Earth with the same acceleration. So you go out and you build a machine and you make observations to investigate some truth about nature. Do you think Newton got his hands dirty with, do you think he got any splinters in his fingers, or he had to use any saws or, hammer and nails? He probably had a quill pen and a Ponzi looking hat, and he probably sat up in his windowsill thinking deep thoughts. The theorist uses mathematics and ideas. Today, they also use computers in place of a calculator. And they both discover the same thing, but each has a special advantage. And if you guys aren't indoctrinated into the world of physics, you might not even realize that there are two varieties of physicists. The experimentalists build machines and make observations. The theorist comes up with ideas in math, but the two are necessary to keep each other in check. In particular, even though Newton was rediscovering something that Galileo had figured out, he did get new insight into the problem that Galileo did not have. For instance, let's imagine that Newton and Galileo go to Mars, and both of them want to discover what little g is. Galileo would either have to bring his inclined plane, or he'd have to build one on Mars, and he'd have to roll the spheres again and do all of the observations and compute the new value. Newton, provided he could get a good estimate of the mass and radius of Mars, Newton can now see that little g on other worlds does not depend upon the apple, or remember I showed you guys the video with the hammer and the feather? Did we do that last time? I did do that. So if you know the mass and the radius, you can now see, not only can you calculate what the little g is, but you now learn something about little g itself. You learn that little g is based upon the mass of a planet and the radius of a planet and big G, and that's it. Conclusively proving that the material that's falling, whether it's a hammer or a feather, does not affect it. In other words, even though you're going over the same territory again, you're going over it a little bit deeper. And my point is that there's something to be gained by combining the laws of motion and the laws of gravity to rediscover a truth that was already somewhat known. You get extra insight into it. Now, today in modern science, these two scientists work hand in hand to keep each other in check. So if I were to go to a modern talk on astronomy or in physics, the way it would work is experimentalists would go out and make some observation, say about the rotation of galaxies. And then they would say, hey, theorists, could you do some math and calculate this and see if what we're saying makes sense? And they will try to derive a model that matches those observations. If they can get the two to work together, then they have a pretty good feeling about what's going on. Sometimes a theorist say, actually, it should be rotating like this. Is it possible that you made a mistake in your observations? And they'll go back and check. And then they'll say, actually, it just doesn't rotate like that. It rotates like this. Is it possible you made a mistake in your math? And the two of them, in an ideal world, keep each other in check. This is how modern science works. Okay. That was a cute little exercise to tell you about little g and how you can use Newton's laws of gravity and motion to rediscover some truths. And that was the spirit with which Isaac Newton rederived Kepler's laws. And I came to this at the end of last lecture, but I did it so hastily that I felt like we needed to go over it slowly and carefully today. Also, this stuff is going to be on the test. So let's have a section called Newton's version of Kepler's laws. And these are Kepler's laws of planetary motion. It's also a chance for you guys to flex and show me that you remember things that we've talked about. So let's start with Kepler's first law of motion. I'm going to call all of these NK1, NK2, and NK3 to remind us that these are Newton's modifications to Kepler's laws. But you guys can start by telling me what the Kepler version is. What was Kepler's first law of planetary motion?
It was the law of ellipse.
Okay, and let me get a picture up so that as you read this, where is my toolbar? I just want something to hold on to. Okay, so why don't you read that out to me, slide 58. Jenna.
Okay. A planet orbits the sun on an ellipse with the sun located at a focus point.
Excellent. Now that was Kepler's version. Kepler, as you recall, was only interested in trying to fully model a Copernicus-like solar system with planets going around the sun. And he found that he could make it work if he put the sun at a focus point and let the planet orbit on an ellipse. Newton discovered that if you included gravity in your calculations, a much more sophisticated picture shows up. For instance, while it's obvious that moons are going to orbit on ellipses as well, Newton now realized that you could have more exotic situations. For instance, what if you had, instead of a giant sun and a little planet, what if you had two binary stars that had the same mass? Now you would have a little bit of a riddle on your hands, because if the two masses were M1 and M2, you might start to wonder, well, hold on a second. Does mass 1 orbit mass 2 on an ellipse with mass 2 at the focus point? Or would instead mass 2 orbit mass 1 on an ellipse with mass 1 at the focus point?
You confused me on that one because I know there's rotating stars, right? The
There
big
are
Dipper has a
binary
rotating
stars.
star on itself.
So John, try to use your physical intuition, and what do you think would happen? How would it work?
Wouldn't they rotate around each other, kind of thing?
That's true. But now suppose we want to state it precisely the way Kepler's laws are stated. What would be at the focus point? Would what?
Just their gravity.
Pardon?
Just their gravity towards one another would be at the center?
Gravity is kind of a gossamer abstract concept. How can gravity be at a focus point? You know what I mean? Something like that. I'm not saying you're wrong. There is the essence of what you're saying might be true, but we need to do better in terms of stating it precisely. Okay, I'm just trying to show you that it's complicated to think this up the first time, right? It's not immediately obvious. You have to do the calculation. And what you discovered is what Newton discovered is something like what John said, but let's put a concrete description of it. He realized that both objects would orbit on ellipses about a common center of mass. So let's see how the center of mass thing works. If you have two stars and they are equal in mass, like a pair of binary stars, then the center of mass would be dead center in between them. And that would be at the focus point, an invisible point that was the center of mass. The center of mass is kind of like the middle, but it's weighted by their respective masses. For instance, in the second configuration, let's say star 1 was 4 times as massive as star 2. Then the center of mass would shift to 1/4 of the distance between the two. If the center of mass was 10 times greater, the center of mass would shift to 1/10 the distance. It's the center, but weighted by their respective masses, if that makes any sense. You know, in the case of the sun and planet Earth, the sun is literally millions of times, 1 million times more massive than Earth. So there is a center of mass between Earth and the sun, but it's so close to the center of the sun. I think it's about, well, think about it. What's 1/1,000,000 of 150 million kilometers? It's 150 kilometers. But do you know what the radius of the sun is? The radius of the sun is 700,000 kilometers. So the center of mass of the Earth-Sun system is a point inside the belly of the sun. And therefore, technically speaking, Kepler's first law is a lie. It's not true for Earth and the sun. The truth goes more like this. Earth orbits a point inside the belly of the sun on an ellipse with a point inside the belly of the sun at a focus point. Oh, and the sun orbits a point inside the belly of the sun on an ellipse with a point inside the belly of the sun at the focus point. Or in other words, to put it more plainly, Earth and sun wobble around a common center of mass. The sun wobbles on its axis due to gravitational tugs from the other planet. This is known in astronomy as stellar wobble, and it has a lot of different cool applications in modern astrophysics. We use the fact that planets cause their stars to wobble as a method of finding planets outside of our solar system. The planets that we've discovered outside of our solar system are much too far away and much too faint for us to be able to detect them with a modern, powerful telescope. We can only see the light from the stars. So what we do usually is we get a powerful telescope, and one of the ones that's the biggest planet hunter out there would be, well, historically has been the they've named it after Johannes Kepler, ironically, the Kepler Space Telescope. And the science mission of the Kepler Space Telescope was just to find planets outside of our solar system. And it did this by taking a big ass telescope, putting it into space, and staring at thousands of stars at the same time and waiting for those stars to start wobbling. And when the stars started to wobble, slide 68, then they would infer the mass of the planet from the amount of wobble. So which planet do you think causes our sun to wobble the most?
Would it be Jupiter?
That's right. The first order wobble of the sun is caused by Jupiter. Weirdly enough, the second order wobble, the second most important one, I think is tied between Saturn and Earth. Saturn is 10 times more massive. Sorry, Saturn is 100 times more massive than Earth. But
But it's
Saturn
further-
is 10 times farther away. And because gravity falls off as 1 over d squared, 10 squared is 100. So Saturn is 100 times more massive, but the distance is weakens the force by a factor of 100. So both Saturn and Earth cause the second wobble of the sun, and all of the other planets combined make a tertiary wobble. Because our solar system is a multi-planet solar system, if you were to watch the true wobble of the sun in real time, it would probably trace out a quite complex rosette pattern, which was the combination of all the different planets causing it to wobble. And there are astronomers who make mathematical algorithms to take that crazy spiral wobble and deconstruct it into a number of planets. That's how we've discovered multiple planets outside of our solar system. Anyone remember how many planets we found? You know, I'm 42. When I was a student, the number of planets that we knew to exist outside of our solar system, 0. They weren't even sure if planets were a freak of nature or they were normal. When I was a student, there was literally a debate which was, we of course suspected maybe all these other stars have planets, but we couldn't prove it. Maybe planets were just a freak accident. And the fact that there's life in this solar system was a blessing from Hosanna or something. Guess how many we know to exist today? John, did you guess or?
I was just thinking Trump when he was saying billions and billions and billions.
No. 5,000, a little over 5,000 is the count today. To me, that seems impressive because when I was a student, we didn't know about any planets that existed outside of our solar system. So for me, in my short lifetime, getting longer, to have seen it go from 0 to over 5,000, that's impressive to me. Maybe it's not as impressive to you guys. I don't know. Okay, one other thing. Not only was it possible, oh, by the way, you guys will notice that the whole point of Kepler's laws was that planets orbit on ellipses. Here you can see the planet and the sun are on circular orbits. Technically speaking, a circle is a special class of an ellipse. If the planets had high eccentricities, this is what it would look like for a binary star system in which both planets orbit on ellipses. But I'd like you to notice that the focus point F1 of one star system is the focal point F2 for the other star. So they're always orbiting in such a way where the center of mass between them, let's just grab it on a particular point here. The line between them always cuts through the center of mass. I think that's pretty cool, all right? The center of mass is always on a line between them. So they're doing this kind of complicated bee dance, which is quite beautiful. Newton discovered one other thing. Not only was it possible for the planets to have a center of mass as the focus point, but he also discovered that it was possible to have unbound orbits as well. And that in addition to circles and ellipses, you could also have these kind of unbound orbits where planets could slingshot past a star on a parabola or a hyperbola. These are examples of unbound orbits, orbits that do not close on themselves, but the velocity of the comet or the spacecraft is so high that it kind of just slingshots off the star and flings out into space, never to return. Kepler could not have imagined such a thing as an unbound orbit. It just wouldn't have fit into his worldview. But now, Newton could conceive of the idea of one gravitational object getting deflected by another's mass and flinging out into space. Today, we use this in all of our spacecrafts, either to build up and accelerate them into the outer solar system, or to slow them down when we want to reduce their velocities when they approach another planet. And as just a simple case in point, I don't know, the Perseverance might have actually had a couple of slingshots to slow it down, but one that I know I can find pretty easily on the internet would be the trajectory of the Voyager spacecrafts. So Voyager 2 orbit or trajectory. Let's see if I can find this here. When we sent Voyager 2 to the outer solar system, I want this picture, but I want it bigger. We launched these spacecraft in the late 70s, and as they made their journey first to Jupiter, Saturn, and in the case of Voyager 2, it actually passed Uranus and Neptune. Each time they went past one of these planets, they would use the gravity of the planet to get a freebie, a free boost of speed. Every time they passed by a planet, they'd have the spacecraft slingshot off on one of these unbound orbits and grab some extra velocity from the gravity of the planet. Today, these two spacecraft are still in operation. They've since left the edge of our solar system and are now some of the only man-made objects to have traveled outside of the solar system into deep space, where one day they could potentially be picked up by aliens, or who knows what their fate will be. But they're forever being flung out into the cosmos, and they're still sending very weak radio signals back to Earth, reporting on the density of particles and the magnetic field conditions. It's a science mission that's still going today. It's incredible. Let's write down Newton's version. I got a little carried away there. Let's write down what Newton's version of Kepler's first law is. Two objects orbit. I guess I shouldn't say objects, I should say masses. Two masses orbit each other on an, now what I would like to say is ellipse, but I'm going to make use of strike through there to remind us that it's not an ellipse, it's what we would call a conic section. Two masses orbit each other on a conic section with the center of mass at a focus point. So I'm getting a little distracted, guys, because there's some kind of wild protest going on outside. I don't know what's happening, but there's some ruckus or commotion out there. Okay. Kepler's second law. How am I doing on time here? Probably bad. Can you guys hear that? Or I don't think the audio is picking that up, is it?
Did you start a riot again?
I'm worried about that, yeah. Oh my God. I don't know if it's a Jesus freak or what's going on, but somebody's got a megaphone and they're going ham out there, guys. So it's kind of rattling me because I'm trying to focus on this and I can hear them going holy hell out there. All right. How about Kepler's second law? Can anyone remember that?
It's the law of areas.
Okay, and why don't you read that out for us, Jenna?
A planet sweeps out equal units of area in equal intervals of time.
Yeah, sorry, I'm just looking. Oh my God, it's just getting louder and louder. They're shouting that your body is 80% water. Maybe it's a science lecture. Maybe it's a competing science lecture. I won't broach it. I won't stand for it. Oh my God, it's a Jesus freak screaming about radiation. All right. Shut the fuck up. People are trying to work. Sorry, guys, but I don't need that in my fucking neighborhood. I just don't. When Newton investigated Kepler's second law, he actually discovered that this law needed no improvement. Okay, the law. So that what we would call it is, they sometimes call it the law of equal areas, but it's equal areas in equal times. That's like the short version of it. And Newton discovered that when he analyzed the math, that this law was true and it needed no alterations to be complete. But just as with the calculation of little g, he could see a little bit deeper into the problem, he discovered there was a reason why planets sweep out equal areas in equal times, and it has something to do with the conservation of angular momentum. Oh my God, this is outrageous. I am normally not a call the cops kind of guy, but I'm this close. I'm this close.
Throw some water balloons on them.
I mean, I would, but they'll sue me. You know how these people are. They'll call 44444, call Jack, fight back. You know what I mean? And suddenly I'm the bad guy.
Tell them you give back their 8% water.
Here's your 80% water right here, buddy. Oh my God, that's too good. That's too good. All right, they're drifting away. Fucking assholes, man. Never give someone a lecture they didn't pay for. That's my motto. All right. And finally, I'm going to talk more about the conservation of angular momentum next time, because I'm obviously not using my time very well today. The real big kahuna is getting to the third law of Kepler and seeing how Newton modified it. This is something we've already talked about, but we need to talk about it some more. Do you guys mind if I erase these two? All right. All right, introducing the big kahuna. It's known as Newton's version of Kepler's third law. And this is a really important topic. In fact, in some ways, guys, all of the stuff you've learned about Sir Isaac Newton, the law of gravity, the laws of motion, they were all building up to this. This whole chapter is an excuse to get to this formula. Remember that in Kepler's third law, you had this simple equation, p squared equals a cubed. You are going to need to use this on the test, guys. And here's some practical stuff that you need to know. Let me rewrite that. I don't like my handwriting here. P squared is equal to a cubed. The important thing is that P must be measured in years and A must be measured in AUs. That's one of the important things. Also, you guys know what P and A stand for here, right? What does it stand for?
Period and distance.
Great, period and distance. And as I mentioned last time, this only works for orbits that go around the sun or equal mass star, something that has the same mass as the sun. But for the most part, it only works for planets going around the sun. It will work for planets. It'll work for comets. It will not work for moons. It will not work for satellites. It will not work for binary stars. You guys will remember that I told you an anecdote from the history of astronomy about the fact that at some point, and I would like to get the slideshow to help here, remember that one of the observations Galileo made was that there were moons orbiting around the planet Jupiter. And that he wrote Kepler a letter, and let me just find the slide from his notes to burn it into your brain. Slide 79. Slide 79. Slide 79. Okay. Galileo had watched moons orbiting around the planet Jupiter, and he wrote a letter, a famous letter to Kepler saying, Kepler, I know you're a fellow enthusiast who believes in the Copernican solar system. What do you think about the fact that I found moons orbiting around the planet Jupiter? Kepler's first thought was, Galileo, could you try out p squared equals a cubed? And could you see if my formula works for these moons? And Galileo did this. He measured the distance between the moon and the planet. He cubed it, and then he squared their periods, and he found it totally didn't work. And it made Galileo lose respect for Kepler and even be suspicious of p squared equals a cubed. Of course, neither one of those men could understand or know at that time that because the mass of Jupiter is not the same as the sun, this equation would not be sufficient. Kepler accidentally made this equation work by inventing the astronomical unit. In general, if you want to know the real version, the Newton version, you have to account for the gravity between the two planets. And when you do that, you get what I call NK3, Newton's version of Kepler's third law. P squared, and you've seen this before, is 4 pi squared a cubed over g times the sum of the two masses. This is the version that works for any two orbiting objects, including planets around the sun, works for any two masses which are in orbit. A reminder that it does use MKS units, that's not an abstract point. That's going to matter to you during the test because you're going to have to convert to MKS, just like we did today with Jenna. You are going to want your period to be in seconds. You're going to want your distance to be in meters. And you're going to want your masses to be in kilograms. Why, might you ask, don't I just use this formula all the time? Well, I could. Can anyone think of a reason why I'd prefer to use this formula if I could?
It's more accurate because there's less.
Nope, the accuracy is the same. You
Oh.
get the exact same answer. The accuracy is the same.
Not more accurate. I meant to say there's less room for error since it's a simpler equation.
Okay, yeah. So it's easier. In other words, easier to punch into your calculator. Fewer calculator mistakes, I think is what you're saying, Jeff. And that would be a good student way of looking at it. So I approve of that. Okay. When you can, on the test, if I ask you to find the period of a planet going around the sun, you should totally use this because it's way faster and way, as Jenna says, less room for mistakes. If I ask you to find the period of a satellite going around a planet, you're going to have to use this one, right? There's another aspect to this that you guys haven't heard about yet. We're going to practice calculating the period of the International Space Station as part of our lab today. So we're going to practice using this formula the way it's written here to calculate a period. But the point that I have to tell you today, that's the new material, you can think of this as the first time I'm getting to some really new stuff today. This version of NK3 is not the reason you're learning it. It's not why astronomers love this formula. Let's take a look at the variables versus the constants in this equation. This part of the equation, 4 pi g squared, those are fixed numbers. They're what we call constants. And those never change from situation to situation. It's basically a single number. The parts of the equation that do change, and let's write it in terms of a proportionality argument. You'll remember I did this for you guys as an exercise in our homework. P squared is proportional to a cubed divided by the total mass of the system. Those are the variables that matter. At this point, I would like to have an adult science conversation with you guys. Of these three variables, period, distance, and mass, if you were an actual well, in astronomy, we don't call them experimentalists, we call them observationalists. Let's say that you're an observational astronomer like Galileo, and it's your job to actually look through the telescope and see the planet and watch the moons going around it. Which of these quantities do you think would be the easiest to measure with your eyeballs? Period, distance, or mass?
Period.
Yeah, and if that's Paul G back there, how would you measure the period, Paul? I would actually like to talk about it. Let's look at Galileo's notes. How would you go about measuring the period of these moons from Galileo's notebook here? Does that question make sense, or is that too weird?
What I would do is just time how long it takes to get from the starting point all the way around back to the way it was.
True. And where would you choose your starting point?
I can use this first one at the top and go all the way down to this number 3. I think that's a 3, the first 3.
Yeah.
That would be a period because, oh, actually, no, there's 3 moons, not 2 moons.
There's actually 4, but you can see he sees, sometimes one of them is hidden behind Jupiter. I guess the point I was trying to make, Paul, is even measuring the period, you have to stop and think about it. Where do I start and stop the measurement? I can think of 2 different ways, Paul. One would be to try to wait until the moon gets to its greatest elongation, whatever that was. You'd have to watch it go behind the planet and back. So you can see if you were focusing on Io here, it looks like oh, I see what you said. You were saying the third one down. So here you're saying it comes back to the starting position. Was that your idea?
No, the one after that, because we're back to 2 moons, but then I just realized there's more than 2 moons.
Right, there's 4. But anyways, I'm just trying to say, even doing something simple like measuring the period when you actually try to do it, is in itself more complicated than you might think at first. But in any case, Paul had the correct answer. The period is the easiest thing to measure because at least you can see the moons going around the planet, and you can attempt to say, okay, I'll start it when it's over here, and I'll wait till it comes back to the same position again. In other words, in the language of adult science, period is what we would call the observable. And that's a loaded word in science, in astronomy, or in physics. The observable is the thing that the scientists, the experimentalist, can measure. Why the hell would you solve an equation for the observable? I mean, suppose you guys had an option, look through a telescope or do math. Which one do you pick? I was thinking that would be an easy question to answer.
Telescope.
Yeah, I'd much rather look through a telescope than do math. And I'm an astronomer, right? You'd never calculate the period. This is a useless version of this equation. What do you think is the second easiest to measure? Mass or distance? John says distance. But even then, John, you might, and this could matter because there may be a little question like this on your exam, okay? Measuring the distance might not be what you think it is. When you're looking through your telescope and you're observing a moon separated from a planet, this is not a distance. This is an angle. That's an angle. Remember, the angular size of Jupiter is probably 1 arc minute. So if this is an arc minute, I'm guessing this moon is maybe 2 arc minutes or 2.5 arc minutes from the center of Jupiter. So what you'd have to do to get A would be a little more complicated. Watch this. So what you'd have to do is, here's Jupiter, here's the moon. You're observing it from down, oh, let me try to do that again. You're observing it from far away at Earth. And you'd actually have to use the small angle formula. If this is what you want, if this is A, your separation, you'd actually measure the angle between the planet and the moon. You'd have to know the distance to the planet. First, you'd have to use the small angle formula and convert from an angle into a distance. Do you see how that makes A just a little bit more complicated? However, it is still an observable because the angle is an observable, and then you can use the angle to get the distance. On the other hand, this thing here, the mass, that's hard. That's not an observable, that's a calculatable. How could you possibly measure the mass of a planet? What do you think you're going to do? Take your Stop and Shop scale out to Jupiter and give it a dunk? Are you going to put it on a balance beam the size of the solar system? The only way we know how to measure the masses of planets is through this formula. That's the purpose of this formula. Let me introduce a new version, the real version of Newton's version of Kepler's third law. I'm going to erase this, okay? Introducing the real version. It's NK3 solved for mass. It's the total mass of my system, M1 plus M2, is equal to 4 times pi squared times a cubed over g times period squared. This version of the formula is so important to astronomers that they even have another nickname for it. You know what the book refers to it as? As the cosmic balance beam. You'll remember that when I talked to you guys about the difference between mass and weight, I told you that masses must be measured on a balance beam. The purpose of this formula is to find the mass. In fact, one of your labs this semester is going to be to calculate the mass of Jupiter by measuring the period and the distance of its 4 moons. We're actually going to do this. That's also how we know the mass of the sun. It's also how we know the masses of all kinds of different things. Hell, there's a famous asteroid that has a little asteroid moon around it, Ida and Dactyl, and we've estimated the mass of the asteroid by watching the moon go around it, measuring its period and measuring its distance. Sorry, I'm getting parched here. You guys have to do this on your test, okay? This is going to be on the test. You'll remember that we did, I think, 2 problems in our homework last time. One, we calculated the mass of Earth, and in one, we calculated the mass of Jupiter. You'll want to study those problems. There'll be problems just like it, and we'll go over that on Wednesday. How are we doing on time? I want to squeeze one last little thing in. Normally, I would have us do a calculation on this, but we're going to do a version of this solving for period in our lab today, and I promise I'll do a practice problem or 2 using this on Wednesday. So let's save it for then. The last thing I wanted to be able to introduce before we take our tea break is just one last quick formula that came up. Unfortunately, today's lecture was me picking up the pieces that I didn't get to last week. And the last piece that we have to do so that we can move on Wednesday is just to have a brief mention about escape velocity. This will also be on the exam next week. I'm going to call the escape velocity V subscript ESC for escape, okay? And I'd like to define it in the following way. That unique speed that any object needs to leave a planet, could also be a star, a planet or a star of mass capital M and radius capital R. Let's write down the formula and then I want to talk about it. The equation for the escape velocity is the square root of 2 times big G times the mass of the planet divided by the radius of the planet. Let's get that into your notes. Here's something weird to think about. Let's use our whiteboard here. As you guys know, one of the things you can do with Newton's law of motion is if you take a cannon or something and you fire a missile or a projectile from that cannon, if you fire it at an angle up into the air, it will travel on a parabola because, as we now know, all gravitational orbits are parabolas or ellipses or hyperbolas. And then it will come to a stop when it falls and hits the ground. If instead you were to fire it horizontally, it will also travel on a parabola, but it'll kind of look like a straight line at first, and then it will sink down to the ground. Now, I think the way that Newton kind of came up with this is he could imagine firing a bullet or a cannon at faster and faster velocities, and the parabola would be wider and wider until the bullet fell to the ground. But imagine that you start to zoom out, and at some point you consider an entire planet's diameter. If I now put a cannon, let's change my color here. If I put a cannon, my mouse drawing skills are somewhat limited, so bear with me here. I can start firing that cannonball faster and faster, and it will travel farther and farther. But Newton at some point must have realized that there would be some critical speed which was so fast that you actually pass the curvature of Earth and you go into a low Earth orbit. Now, one of the things, of course, that makes this difficult is on Earth, you're fighting against the friction of atmosphere. But consider this, the moon has no atmosphere. In theory, if you had a rifle or a gun that could shoot a bullet fast enough at the escape velocity, the bullet could actually travel all the way around the moon, unimpeded by the vacuum of space, and fly around and hit you in the back of the head. In theory, if you could fire a gun at the escape velocity, the bullet would go into a super low spin orbit and you'd shoot yourself in the back of the head eventually. That's a crazy thought, right? And the idea is that from those considerations, you start to realize that it's a velocity, a key velocity that depends only on the mass and the radius of the planet. As our final exercise today, I'll have us calculate the escape velocity of Earth. That's a number that might come up from time to time. In this equation, masses must be in kilograms. The radii must be in meters. And I'd like you guys to just do one quick calculation for me. Find the escape velocity of Earth. And we'll just kind of set it up and I'll put the values right in there for you because I'm running short on time. The escape velocity is 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of Earth, 6 times 10 to the 24 kilograms. And Jenna helped us work out earlier that the radius of Earth in meters is 6.4 million. Can you guys just prove to me one more time that that's something you can handle? I can show you how to put it into the calculator, but of course it's better if you do it on your own. So why don't you punch that up for me? Jenna, show me that you have good rounding skills.
Okay. How many sig figs? 2?
Yeah, when in doubt, choose 2.
Okay. 1.1.
Hold on. Are you about to put this answer into scientific notation? This happens to all my students. You guys get confused about rounding and scientific notation. They're not the same thing. Scientific notation is used when the number is big, over 1 million. Rounding is something you do because you have good taste. Jenna, is your number bigger than 1 million? Well, the
No.
answer is not 1.1, so don't give it to me in scientific notation.
Okay. 11,000 meters per second.
Nice. That's my girl. That's great. 11,000 meters per second. Excellently done. And that's how you would do it on the exam. Now, hold on. I'm worried because no one's sharing video except for Ryan, John, and Jenna. And shame on the rest of you for not participating with, well, some of you don't do the camera thing, but still participate like Ryan and Paul G. So you're in my good graces. But anyone watching at home later who had trouble with that, damn it, it's dark in here now. Okay, watch me do the punch, just in case you didn't get this. 2 times 7 exp negative 11 times 6 exp 24 divide by 6.4 exp6. Then you hit equals, and then we do shift square root. and she rounded that to 11,000, just as she should have. Hopefully that helped some of you. Hey, Jenna, bonus points if you can tell me what that is in kilometers per second. Remember, you had a goof up with meters and kilometers earlier, right? Without doing dimensional analysis, can you guess what the answer is in kilometers per second? Or you could do it on your paper and not show me, whatever.
Is it 11 times 10 to the 6th kilometers
No,
per second?
no. You went the wrong direction again.
Oh, yeah. Yeah, it would be 1.1 kilometers. Or, okay, I give up.
Okay. Let's do it dimensional analysis. We don't give up. We try a new approach. 11,000 meters per second. What units do I want to do here?
Kilometers on top, meters on the bottom.
Good. Now, give me the conversion factor.
1,000 on top and 1 on the bottom.
Okay, punch them up.
So I just have a quick question. Sorry, before you continue. How did you get the? I forgot what it's called. The meters per second. How do you know when? Because I'm still confused on that. Sorry, the noise. I'm at work.
That's okay. Look, whoever you are, I need to
It was
understand.
Yuri.
Yudi, are you saying how did I punch it in and get the number, or are you saying how did I get the units?
The units. Yeah, that's what I meant. I just forgot the name, the word for it.
So in other words, you were trying to balance these out to get that, and you were having trouble? Okay,
Yes. Yeah.
we're going to come back to this in a second. Let's talk about Yudi's thing real quick. Yudi, there are two different methods. Let's talk about the easy method. The easy method is you're calculating a velocity. So one thing you could do, Yudi, is say, well, shit, I know a velocity should be like miles per hour or kilometers per hour, but I know this has to be in MKS units, and MKS units of velocity should always be meters per second. That's one way. The other way is to do the unit dimensional analysis, and I could see that being troubling. So watch this. Do you see meters cubed in meters? This 1 meter will cancel out 2 of those, leaving you with meters squared. Kilograms cancel with kilograms. But look what you have left behind, Yudi. It looks like meters squared per second squared, but do you see the square root? That square root affects the units as well as the numbers. So what you really have is the square root of meters squared per second squared. And if you square root both sides, meters per seconds come out.
Oh, okay. Yeah, that made it more helpful. I was just confused with that.
Sure, because students always forget that the square root applies to the units as well, right? Okay, let's go back to Jenna's thing. Jenna, to quote Brittany, oops, you did it again, okay? Jenna, you made the same mistake that you made at the beginning of our lecture today.
Oh.
See,
I did.
Jenna, you're missing the point. It's not that 1,000 always goes on top and 1 always goes on bottom. It's that you've got to keep the number with its units. Remember I told you that? This matters to you, Jenna, because you're going to be struggling with this come exam time. Let's look at our equation sheet again. I really have to stop this fucking lecture, but look, Jenna, 1 goes with meter. Oh, sorry, forget about that. 1 goes with kilometer. 1,000 goes with meter. Is that what you did?
No, I confused him again. I was just kind of going off of memory, but I would look.
Right, because the last time we were going from kilometers to meters, but you
Yeah.
need to be able to do it in either direction. Watch out for that come the exam time. Okay, so what's the escape velocity in kilometers per second? Take it away, Jenna, or anyone else.
Eleven
Right.
kilometers per second.
It is customary in planetary science, it's customary for us to express escape velocities in kilometers per second because it's a little bit classier than doing it in meters per second. Is 11 kilometers per second fast? Want to see what it is in miles per hour? Watch this. Oh, totally busted here right now. 11 kilometers per second to miles per hour. It's only 25,000 miles an hour. If you could, if you could ride your BMX bike and hit the ramp, if you could travel at 25,000 miles per hour and you launched off of a ramp, in theory, you could ET that shit right out into outer space. You could just fly right out of the atmosphere up into outer space. John works on airplanes. I don't know, maybe he'll find this interesting. If you ever watch an actual rocket launch, when rockets launch from Cape Canaveral, you'll often see them taking this kind of hard left-hand turn. Let's just look at a picture of, say, a shuttle launch. One of the interesting things about our current level of rocket technology, so let's see if we can see one where it's kind of getting a little bit higher up into the sky. There's a nice picture of a shuttle launch as seen from this F-15. I really like shuttle launch. Is it an F-15?
There's a simulator that my son likes to play on his phone. It's
Oh,
a
really?
space flight simulator.
No
You should check
kidding.
that out.
And basically, do you try to do stuff like this, like launch things off the Earth or something?
You have to make little crafts with fuel and everything, and you have to follow the curvature and use it to like slingshot to try and land on Mars. And
These
it's
kids,
crazy.
John, they're going to be so smart. They're going to take our jobs. Before I know it, your son's going to be muscling me out here because I had to see these kids do this for fun while they're eating Cheerios, right? This is awesome. I should really get that because I bet probably adults would have fun with that too, right, John?
Thing drove me nuts.
So one of the things I just want to explain what's going on here, and your son might actually know more about this than I do, hell. At our current limit of rocket technology, because you have to fill the rocket up with this solid oxygen booster, it adds mass to your rocket and makes it harder and harder to accelerate. Our current limit, as far as I understand, we are only able to really power rockets up to about 10 kilometers per second. We don't have the technology to really jack them up to 11 kilometers per second. So in theory, we should not be able to leave Earth. Here's where it gets crazy. On a spinning Earth, you actually have a velocity through space. And the closer you get to the equator, the faster your velocity is because you're traveling a bigger and bigger circle in 24 hours. At roughly the latitude of Cape Canaveral, Florida, your velocity through space is just about 1 kilometer per second. So the way that we get these shuttles into space is you fire them at 10 kilometers per second into the spin of Earth, and the spin of Earth gives you the last click per second that you actually need to get into orbit. So that's why in your son's simulator, or in this cool picture as taken from an F-15 or something, if I got the wrong jet, John, I'm sorry, I'm not, versed in these things. You can see the rocket leaning into the curvature of Earth because they're getting that that last kilometer per second boost from the spin of Earth. If our Earth rotated as slow as Venus, it's doubtful that we ever would have been able to get to the moon. Venus has, for instance, all the same mass and radius as Earth, but almost no rotation. If we had grown up on the surface of Venus, I don't think Neil Armstrong and Buzz Aldrin would have made it to the moon. We just happen to have the right spin where we can get that last kilometer per second to get into space. Kind of cool. Look, I could tell you more stories, but I'm totally over my budget right now. Oh my God, a 142. Okay. So here's what's going to happen. We've got a short and easy lab that's good practice for the exam. It's on calculating the period of the International Space Station. All you're going to need for today's lab is a nice piece of graph paper or just some kind of nice paper. We're going to make, if you have a compass to make a nice circle, that would be cool, or a little coffee lid or something, and then a calculator and a ruler. So make sure you have a ruler, something to make a circle with, and some paper and a pencil, okay? By the way, another important announcement. I'm sick of grading people's typed homeworks because there's a couple of people that do it right, but there's a lot of people that are doing it wrong. If I yelled at you in your last homework because I didn't like the way you were typing stuff, then please could you just use paper and pencil so that I can read what you're doing? Some people were literally writing out p squared, like the word squared, equals a cubed. I can't deal with that, all right? So that's not okay. Anyways, let's take a 15-minute break. iPhone time is now 1:45, so at 2 o'clock we'll begin, and I'm sure we'll be done before 3, okay? All right, I'll see you guys then. Hello, everyone. We're back, and it's time for lab. Today's lab, lab number 5, is on calculating the period of the International Space Station. Let me just make sure I'm doing that right. You don't really need any special handout for today. You're just going to need a nice piece of paper. You can do it in your notebooks. You need your calculator, pencil. A ruler is really helpful, as is a good circle maker. You could use a coffee lid or a roll of tape if you can't find anything else. The idea is that you guys need lots of practice with Newton's version of Kepler's third law. I found this really helpful to do in lab when I used to hang out with you guys in a classroom, because most of you are sucky at calculator stuff, and then you try to hide from me as if you think you're helping yourself by sneaking away and, oh, I'll never notice that you didn't get the right answer. The only person you're hurting is yourself. I already know how to do this stuff. I want to make sure that you guys can actually punch it into the calculator. Now, if only Jenna and John are hanging out with me live here, this is going to kind of irk me a little bit. So I hope the rest of you, thank you, Ryan, someone like hang out with me for God's sake, so I'm not wasting my time. If you guys get to a point where you just want to troll and you don't want to participate, I have recordings already made that I can share with you. I want to make sure that you guys can punch it into your calculator. You should all, oh, thank you, Amanda. What's up with this kitty here?
He's mean and he's also gagging, so he might puke on me right now. So.
Well, we need to spice up this lab here today. So what's the name of your cat again? I can't remember if we asked.
His name is Poppy.
Poppy. Cool. All right. Well, Poppy's in the house. Thank you for sharing, Amanda. I have a really nice piece of graph paper that I'm going to use when I do my fanciest physics work. When I am a student in a class, I like to just have some really gourmet, fancy graph paper. Having some nice materials helps you get into doing schoolwork. A nice pen or pencil, some tools, you got to kind of geek out on this stuff. So although we've done similar calculations, remember the exam is a week from now, and I could see that being a source of anxiety for many of you. The more practice we get with this stuff, the stronger you're going to be. So part of this is to understand how we apply NK3 again. And part of this is practicing the calculator, just making sure that you got the skills to succeed. I'm going to tear this guy out. Okay. And I'm charging up my phone here, but I should be ready to connect. Let's talk once I share this, it's very hard to unshare it or it'll freak out on me. So let's talk about the concept, how this could be an interesting exercise. Many of you have heard me refer to the International Space Station before, but if you don't know, sorry, my ability to stream internet will be restricted by the number of tabs I have open, I think. So I'm trying to just reduce that a little bit. Okay, if I type ISS into Google, the first thing that comes up is the International Space Station. And if you didn't know this, the ISS, the International Space Station, is a worldwide collaboration between space agencies such as NASA, the Russian Space Agency, the European Space Agency, even the Japanese and others have well, the Japanese have a module. I'm not sure exactly how many partners there are, but it's certainly an international coalition of space agencies that are working to build America's first orbiting space station. And people live on this thing year round. It flies over the Earth in a polar orbit, North Pole to South Pole. And not only is it cool, like you can watch people doing their day-to-day activities on the ISS, like for instance, YouTube ISS. I think I've told you guys that there are these videos where you can watch people doing stuff in microgravity. I think his name is Chris Hadfield. And he makes all these kind of cool videos on just different things, like how to brush your teeth in space. So my point is we can watch videos of people doing fun stuff in microgravity. Also, you can see the International Space Station fly overhead in your local sky if you kind of know when to look. Oh, look at that droplet of water coming out there. I'm sure it's such a treat. Look how the water just, sticks to the toothbrush due to its cohesive forces. Without gravity, things behave a little bit weird. Some of those videos are real fun, and they're only a few minutes, like 3 minutes long, so definitely check them out. In addition to fun videos like that, you can actually see this thing fly overhead at night if you know where and when to look. I've seen the ISS go over countless number of times. It looks like an extremely bright star, much brighter than even a planet sometimes. And you'll just see this thing hauling ass across the sky. You can tell it's not an airplane. It's much too high up. But you know it's not a star or a planet because it's just traveling way faster than the other background stars. And it's not rotating east-west with the sky. It's rotating north to south. If you've never seen it, it's a cool thing to look for. I thought that could be a nice example of how we could use NK3 to calculate the period of the ISS if we know a few basic things from our lecture, the mass of Earth, the radius of Earth. So let's get started here. And this phone seems somewhat charged now. So let me share screen, iPhone, and hopefully this all works today. Okay, looks good. Just kind of takes a minute to connect here. Come on, baby, don't let me down. All right, there we go. All right, lovely. And I'm going to try to use my tape here to balance this thing. I can have hands-free operation. So let's do the thing that we always do at the top of our labs. We're going to put our name. Okay. And let me bring up the lights a little bit. Okay. We're, of course, in Astronomy 1010. This is helpful for me and for you. Your section number would be greatly appreciated, 001, 002, or some of you are in 104. And of course, this is lab number 5. Make sure you upload it to lab number 5. And the title of today's lab is, we'll just make it short, the period of the ISS. A cheap little exercise in Newton's version of Kepler's third law that will be very useful practice for the exam, if you know what I'm saying. All right. So why don't we start by drawing our photo or our kind of cartoon image of what's going to happen. I'm going to do this since we're doing a nice lab together. I'm going to make it fancy, and I'm going to use a compass to draw a nice model of the Earth. I don't know what I'll set this to, but let's say maybe 5 centimeters or so. Now, if you don't have to make it the same size, but I consider the drawing to be a part of this lab. Don't do the drawing, expect to lose 4 or 5 points. That'll tick me off, okay? So make the drawing, that's part of this exercise. I think I'm gonna make my radius 2.5, no, 3 is a little big. I'm going to make it about 2.5 centimeters. If you have a coffee lid or a roll of tape, it should be about the same. So just find anything you can make a circle with. I'm going to do mine all nice because why not? I'll put the center of the planet right there on this crosshairs. That's a nice thing about using graph paper too. It's good for scale diagrams. Oh, look at that. My circle fits perfectly in this box. 2.5 centimeters was a damn fine choice. I'm going over it a few times so it's nice and dark and it'll show up clearly in the video. All right. All right. Now what I'm going to do is I'm going to draw in, just like I did in escape velocity. Hold on, I want to find a little box to lean this up against. I keep experimenting with different ways to make this hands-free. Will that balance? Kind of. All right. I'm going to, fudge on a stick. Okay. I guess you guys can kind of see that. I'm going to draw in the radius of Earth vertically. There's a reason for vertical. Okay. And I'm going to label this R circle with a cross because that's Earth. All right. Radius of Earth. And of course, we know the value of that. The radius of Earth, 6,400 kilometers. All right. And then we have the mass of Earth down here. Once again, the symbol for Earth is a circle with a cross. 6 times 10 to the 24 kilograms. Now let's draw in the International Space Station. Here's how I like to do that. I'm going to draw a small line above, maybe about this high. Okay. I'm going to extend the radius of Earth. And I don't have really good art skills. I was never blessed with that talent. So I'm going to kind of make mine look like a piece of candy. It's going to have like a little module here. And sometimes when I want to make a space shuttle, I put some solar panels on it. Kind of looks like a piece of candy, but it's really supposed to be a satellite with some solar panels. That's the best I can do. This is the orbital height of the space shuttle H. And in the case of the International Space Station, I'm pretty sure it's 400 kilometers is its height above the surface of Earth. So let's label that in. Does that look kind of clear and clean to everyone? I also happen to know the mass of the ISS. The mass of the ISS is 400 metric tons. Does anyone know what a ton is? A metric ton?
Is 1 ton 2,000 pounds?
1,000. Sorry, 1,000. Well, maybe an imperial ton is. A metric ton is 1,000 kilograms. I'm pretty sure. Let's just verify that. Oh, I can't open up my metric. I know this. I don't know why I'm looking it up. Sometimes you have doubts. Oh, actually, very good, John. It is 2,200 pounds, but it's also 1,000 kilograms. Okay, so we were both right. For some reason, I have trouble with the imperial unit system because I was
basing it on like wheel axles and bridges and cars' weight.
Okay, all right, cool. Yeah, well, I figured, especially being a mechanic, you might have some background experience that would be relevant here. Hold on. I just want to. I don't know what you guys can see. If you can definitely see the screen, my iPhone screen. I don't know if you can also see. Can you see my background, or can you just see the iPhone? What do you guys see right now?
Just the iPhone.
Yeah, just iPhone.
You don't see like the background picture. Okay, I was trying to get a nice background. It doesn't matter though. I don't know what people see in the recording. It's because I'm always making it. I'm never watching it. Okay. So 400 tons. If a ton is 1,000 kilograms, then that's 400,000 kilograms. Sound good? We'll keep the pounds for our mechanic friends. So here's our setup. And let me focus this. All right. Does everyone think they have all that intel? That's all the givens. And let's make sure that we understand the question that's being asked. The goal of today's lab is to find the period, how often, sorry about my handwriting, of the ISS. Man, I'm having a shitty handwriting day. It must be because I frazzled my nerves last night. Okay, here we go. ISS. Find the period of the ISS from the givens. And the givens, of course, are over here to the left. We made them as part of our diagram. Those are the givens. All right. This is, of course, a job for Newton's version of Kepler's third law. Let's write it down because you can never write this thing enough times in this class. P squared is equal to 4 times pi squared times a cubed divided by g. And what do you think? I guess the two masses here would be the mass of Earth and the mass of ISS. So let's label that. Mass of Earth plus mass of ISS. Of course, when we set this up, why don't we do the algebra first? We're going to have to remember to deal with that square. I don't want you guys to forget that that's p squared. So, of course, when we solve for the period p, we will get the nice, big, neat square root of 4 times pi squared times a cubed divided by g times the sum of the mass of Earth plus the mass of the ISS. I'm just going to let you guys catch up to me here.
Is there a reason you go back and forth between X's and dots for multiply, or just to drive me nuts?
No, just to drive you nuts. Sorry, Amanda. In higher level mathematics, there is a difference. You know what I'm constantly worried about, Amanda? I'm actually concerned. I do think about it a little bit. Sometimes I'm worried that you're gonna, since you don't know the formulas as well as me, that you might accidentally mistake this for a variable like X. That's
Right.
a concern. Other times I'm worried that you might mistake this for a decimal point. So sometimes what you'll see me doing is when there's variables, I usually use dots, so you know it's not an X. And when it's numbers, I tend to use times. However, at the bottom here, who knows why I did that? I was just being crazy, all right? So they mean the same thing. Stylistically, it would be good to be consistent. I feel you on that. Okay, let's start by, we have to, the problem that you always have when you have to do these problems, when you're doing them on your own, and by the way, you guys really, unless you're like, Amanda took the other part of my course, 1020, a while back, and I think Paul G out there might have taken 1020 as well. But a lot of you have not had the experience yet where you've had to try to do these without my help, and you're gonna find that it's way freaking harder. That's the reason why we're going to practice together on Wednesday, because you guys really haven't had the experience that much of trying to do this on your own. You're going to find it's way harder than it looks when I'm doing it. So what's going to happen to you is you're going to look at the equation, assuming you can find the right one, and you're going to have to be like, well, what is A and what are all these things? Let's talk about the A first. Is it obvious to you guys what A is?
A isn't given it, right?
I'm sorry, could you say that one more time?
A wouldn't be given because we don't know how. With oh no, A stands for area. Sorry.
So, no, A does not stand for area. So this is
Oh.
step, is that Ryan? We're talking to you,
Yes.
right?
Yes.
Ryan, A is not area. Remember, I guess I can't. A is the semi-major axis of the orbit. But usually what that means, because planetary orbits are usually close to circular, A is like the radius of the orbit. Remember, Ryan, that the
Okay.
semi-major axis of a circular orbit is just its radius. So this is a good point, Ryan. You should think of A as being like the radius of orbit, not area, okay?
All right. Yep.
So in that case, Ryan, what's A?
It would be. Would it be 6,400 kilometers plus 400 kilometers?
Very good. I was wondering if you were going to figure that out. It's the center to center distance, assuming the satellite doesn't have a significant width compared to Earth. This height is a good enough chunk. Obviously, 400 is a lot less than 6,400, but it's kind of a big enough chunk where we should consider it. So A, and why don't we label this here, because that might not be obvious to everyone. You are exactly right, Ryan. It's the radius of Earth plus the height of the shuttle. So I'm going to write that down here. And Ryan, can I impose on you one more time, please? Would you be...
Sure.
So here's what I need you to do. We'll first write this down. Sorry, guys, I'm wiggling all over the place. That works. 6,400 plus 400 kilometers. And obvi, that's 6,800 kilometers. But Ryan, I'm going to need you to do something for me here. We cannot use this as it stands for A.
Yep. That because it has to be in meters, right?
Correct. So I was wondering if you would help me do that just to keep practicing.
All right. So it would be 60,000 times
6,800.
6,800. Sorry.
Or 6,800, whatever you want to say.
6,800 times a division bar.
Yep.
Kilometers would be on the bottom and meters would be on top.
Excellent. And the reason, once again, that you know that is because you already have kilometers on top. Only by putting kilometers on bottom will they cancel. And now for step 4, Ryan, you're doing a fantastic job. Let's get our conversion factor and try not to make that mistake that Jenna made a couple of times.
1,000 meters would be on 1,000 would be on top with meters and 1 with the kilometer on bottom.
Excellent. And Jenna, you're never going to make that mistake again, right, buddy?
Exactly. Nope.
In a way, Jenna, making that mistake in today's class was good on 2 levels. It was good for you because it's much better that you make that mistake when we can talk about it, and now you won't do it anymore. But it might have actually been good for the audience to see that mistake too, in hopes that they will learn. Okay, because Jenna, you're not the first person I've ever seen do that before. That's pretty common, okay? Okay, so Ryan, either you can punch it into your calculator or you can do it in your head. Looks like he's punching into his calculator. That's fine. I would do it in my head, but I'm kind of good like that, you know?
Yeah, normally I would, but I just don't want to make a mistake.
Okay, okay, fair. Can I zoom out a little? I can zoom in, but I can't. I guess I have to do this.
That's 6.8 times 10 to the 6.
Units?
Meters.
Okay. So that's in a good usable form. Our A is on lock. We've taken care of that puppy. That's good. You guys know what G is, right? What's big G? Let's write big G down here.
7 times 10 to the negative 11th.
Good. It's always the same number, no matter what the application is. And the units are kind of crazy. Meters cubed per kilogram per second squared. All right. So we got big G. We got, sorry about the glare. We've got 4, we got pi, we got A, we got big G. Now it's time to deal with this. Remember that we can call this mass, this is basically the total mass of the system. Because if you add them together, you get the total mass. It's worthwhile to take a moment to consider the total mass. I'm going to call it M tot, if that's cool with you youngsters. Okay? M tot, mass of Earth, plus the mass of the ISS, equals 6 times 10 to the 24 kilograms, plus 400,000 kilograms. Why don't we go ahead and add those up on our calcies? Amanda's hiding from me now because she knows I'm going to call on her.
I had to find my calculator again.
That's okay. I'm just teasing you. Actually, I would just be happy with anyone who could get me the answer. What'd you get, Jenna?
I got 6 times 10 to the 24th.
Huh, wait a minute, bud.
Yep.
Wasn't that the mass of Earth?
Yes.
How did you add those two and get the mass of Earth?
Because the mass of the ISS is so insignificant compared
Correct.
to the.
You'll remember that we did that a couple of times last class, right? So I was just wondering if you guys would remember, because at some point you're going to have to do this without my help, right? It's cool if you can remember that when one mass is much smaller than the other, you can neglect the smaller mass. Notice when you put it into your calculator, this didn't even show up because this number is so big in comparison. By the way, I'm going to give you another real important tip for the exam. Students who are new to this kind of stuff, they tend to think that this part of the number is the answer, and that's just not correct. When you're trying to find the answer on your multiple choice test, you should always start here. The power is the most important part of an answer. This power is 24 zeros. This power is 5 zeros. 24 is way bigger than 5 zeros. So in other words, basically, the total mass is just the mass of Earth. And we saw that trick many times. So the total mass of Earth, we're just going to end up neglecting this one. Okay, now we're ready to start writing this thing out in all of its grittiness, okay? So P is equal to, I'm going to go ahead and use a ruler just to keep things real neat and tidy. And I'm even going to use a ruler for the square root. Make sure you make a nice, big, neat square root. We don't want no sloppy square roots. I could have even made that lower. Okay, so on the top we have 4 times pi squared times open parentheses. 6.8 million meters is what Ryan got for us. That's got to be cubed. Don't forget about that. Divided by big G. 7 times 10 to the minus 11. The units, which we'll put in, are meters cubed per kilogram per second squared. Here I go, Amanda, with them timeses again. Times the mass of Earth. Six times 10 to the 24. That is a 4 kilograms. Okay. This is the troubled part. Can you actually pull this off? Now, at some point, I'm going to show you how to punch this in again, but it would be very, very useful for you to try it first without my help. If the test were to be taken today, this will determine whether you would be able to get the answer without my help or not. This will also tell me whether this was a useful use of your time or a waste of your time. If everyone can get this, then maybe this wasn't such a helpful exercise. So I want everyone, including all you trolls in the background, to punch this into your calculator and tell me what you're getting. If I had been in a real lab with you, I would have marched around the room and looked at every single person's calculator, and I wouldn't let you leave until you all got it right. Unfortunately, I just cannot police all of you like that anymore. So it's up to you to be honest and work with me. I'll get the iced tea. I want to see something when I'm back. Actually, I switched to water because I'm starting to get the caffeine jitters. Okay, what do you guys got for me? I'm just kidding. This is vodka. All right, whatever. Let me see. Looks like both John and Jenna got it. Ryan, I'm waiting to. Oh, Ryan, are you using a bastard calculator?
Yeah, I
Ryan?
kind of am.
Yeah, and you got a bad result. All right.
Yeah, really.
So Ryan, buddy, Ryan, $8.
Yeah.
Get with the program. But if you
Walmart has it.
huh?
Walmart has it.
Yeah, how much did you pay, John?
$8.50.
Jumping Jesus. What can you get for $8.50 these days? Let me see, Ryan, just because I like you today, because you shared your video and you contributed to class, I'm going to try to help you here, but you're missing the point. If you insist on using a lame calculator like that, you've got to use it to greatest effect. Let me see what the
Yes.
chat people are saying. How do I put this? Do I have a calculator like that somewhere? That's the question. I used to. I think my line entry calculator, the batteries are dead. I'll just have to explain this, I guess. Ryan.
I figured out what I did wrong.
Oh, did you get the right answer?
Yeah, I did.
Can I still give you a piece of advice in case there's anyone else out there with a calculator like yours? In a calculator like that, the beauty of it is you can actually enter all of it in at once and you can see the whole thing and see where you got wrong. What I didn't like when I looked at yours is I could see you getting answers and then doing answer times this square root answer. You're kind of wasting the whole point of the calculator because you can basically see it all laid out in one clean stroke. Do you understand what I mean?
Yeah.
So for your calculator, I'll have to write this out because I can't find my own. I would have done square root, open parentheses, 4 times pi squared times, I would have done the a cubed. Then I would have done divided by the g and then divided by the mass of Earth and then close parentheses. You see what I mean?
Yep.
And do you have the right answer now?
Yes, I do.
Okay, so how should I round it and what are its units?
Oh.
We're going to have to learn to round on our own now. So 2 sig figs, Ryan. Ryan, hold on, buddy. Is your answer bigger than 1 million or less than 1 million? Let's start there.
Hold on, I need to refigure this out. I'm sorry.
Jenna?
5,400 years.
Your number and your rounding are good. Your units are bad. If you look in here, in no part of this equation do you see years. If years don't appear here, they're not going to appear out there. Jenna, let's try to do the dimensional analysis the way that Yudi was doing earlier. What can we cancel out here?
We can cancel out the top meter with and make the meter cubed to meter squared on the bottom.
False.
Oh,
Look.
oh, I see. We can cancel out both meter cubes.
This cube, that's the reason why I write these parentheses in is to remind us that the cube distributes to the meters as well as to the number, right?
Yeah.
So basically what we have here, if I can go onto this page, is we have the square root. Let's get rid of the numbers for a second. We have on top meters cubed. On the bottom, we have meters cubed per kilogram per second squared times a kilogram. So yes, Jenna, meters cubed can cancel. What else?
And then you can also cancel the kilograms.
So what I have now is the square root of 1 over seconds squared. Whoops, focus.
So we're left with just seconds.
That's right, because the bottom of the bottom is the top. That becomes the square root of seconds squared, which is, of course, seconds. Let's box it because that's our answer. On a test, this is as far as you would have to go. I'll have the answers in seconds. You got to get it. However, this is not a test. This is an exercise where we're, oh, by the way, can I just pause here? Ryan, did you really get this? You're causing me doubts here. You're muted, Ryan.
When I saw the numbers on their like what the numbers that they had, I misread them. So I messed up. I figured it out. Oh, come on, people, stop calling me.
But Ryan, I just want you to tell me, honest truth, that you got that number.
I have not got that number yet. I'm
Right, so-
replugging it in now, and
so look,
I should
so-
get the number.
All right, plug it in now, and if not, I have to show you how to do it. Okay?
Yeah, I
Can't get it-
plan on getting a different calculator this week, most likely tomorrow.
Yeah. Do you see? There's usually reasons for all the things I want you guys
Yep.
to do, and you're now learning why I didn't want you to use that calculator. But I will show you how to use it because I like you. This is for all the people in the back and the people at home watching later who want to see how to punch this in. Maybe you're not as good as Jenna or John. So let's see how we do this, okay? We would do 4 times, here's my pi key, pi squared times 6.8 exp6. Now our cube key, we have to hit shift because it's up here. So that's the cube key, yet shift in that. Divided by 7 exp negative 11. Here's the key step. When you get here, you actually have to hit divide. And that goes to you too, Ryan. Divide by 6 exp 24. Then we hit equals. And then we have to square root it by hitting shift square root. So Ryan, you should be punching it in square root, open parentheses. You should do all that shit, but you should do it in one clean shot and then you should close parentheses. Let me show that one more time for the people in the back, this time faster. 4 times pi squared times 6.8 exp6 shift cube divided by 7 exp negative 11 divided by 6 exp 24 equals shift square root. If you cannot get this, there's only one person that you are hurting, and that's you. So you want to make use of my skills so I can show you how to get this done. If you can't do it now, you can't do it on the test. Jenna, my frenna, guess what you're going to help me do? Convert this into a better unit so I can understand what that means. Like if I said, Jenna, let's meet up for a coffee in 5,400 seconds, you'd be like, what? I don't even know what the hell that means, right? So let's convert this into a more reasonable unit. What do you want to convert it into?
Maybe hours.
Sure. Okay, so tell me how to do that.
Okay. All right, so we write down 5,400 seconds.
Okay.
We write times a division bar. We put seconds on the bottom.
Yep.
And minutes on top.
Good.
And we write times and division bar.
Good. I like your moves, kid.
We write minutes on the bottom. And now hours on top.
Damn, I like your funky style. Okay, keep going.
And then equals.
Okay.
Now we cancel out. So we're left with hours. And
Correct.
then we'll put on top 1 minute.
Oh, sorry, bud. I'm trying to do this as best I can. Okay, yeah, keep going.
So 1 on top for 1 minute is equal to 60 seconds on the bottom.
Good.
And then 1 on top 1 hour is 60 minutes. And then we punch.
Yep. And now you divide this divided by that, divided by that. Cool. I like your moves. Your moves are good. Your moves are strong. And tell me what you get.
And then I got 1.5, so 1.5 hours.
Yeah. That's how long it takes the ISS to go around Earth.
You should wear a GoPro with like the little thing that goes on your head and just look down at the paper instead of.
You know what's funny? Guys, you can't even believe it. At the beginning of this pandemic, I shelled out 400 of my own dollars and I bought the GoPro and all this stuff. And I was experimenting with it and it just kept pissing me off. And I kind of just never got back to it. So I actually went through the trouble of spending this money I totally don't have right now on the GoPro. And I even got the stupid head thing. I did that.
I 2 years ago, haven't touched it since I bought it.
Yeah, I did the same thing, and I feel so guilty about that. I had some trouble porting the video over. I was like, I couldn't figure out how to use the thing. Normally, I used to be good at technology, but I think I'm getting old, and I'm getting on the Grampy spectrum where I'm just like, I can't use the damn thing. The buttons don't make no sense anymore. So if any of you guys are good at GoPro stuff and want to come give me a lesson sometime, then for the love of God, I could use your help because I really suck at GoPro stuff. So I know it's, in fact, this camera is an upgrade. One of the students last year was getting rid of his iPhone and gave it to me, and I'm so grateful. Joel, if you're out there, if you're listening, thank you, buddy, for your service, because this has been so much better than last year's camera. Okay, so 1.5 hours. How long does it take us to fly to California or something in an airplane?
Like 6.5, 7.
Right. So do you realize that to go around the entire Earth, 400 kilometers above Earth in 1.5 hours is fucking insane, right? Think about how fast that is. In 90 minutes, the ISS goes around the globe. Does that mean we can see the ISS every 90 minutes? Yes or no?
No.
Why not?
I don't know.
Well, you're right. We can't see it every hour and a half, but there's a simple reason, and I wanted to see if you guys could guess what it was. I'll give you a hint. Here's Earth, right? And
It's
the
on
ISS, huh? John? Wait, no, John, tell us. Oh, he's distracted. Someone talk to me. Someone be my friend.
Is it the angle or the tilt or where we are located on Earth?
Yeah, kind of. Like, let's say this little USB stick is the ISS. It's going in a polar orbit, right? So it's going north to south, just like you see my hand doing right now. But Jenna, how long does it take Earth to spin?
1 day, 24 hours.
Right. And that's way longer than 90 minutes, right? So one of the reasons you can't see it, hold on, let me take the, one of the reasons you can't see it every 90 minutes is you have to wait for yourself to rotate underneath this thing. You've got to wait until Earth actually rotates underneath the ISS. Sorry, there's a wicked hard video lag right now, so I'm getting confused just watching myself. You've got to wait for Earth to spin underneath the ISS. So hold on. Let me make sure everyone's got the final answer, and then I'm going to sum it up with just a quick fun fact here. This is going to be your final product, okay? This is what I want turned in. Sorry about the delay on the camera. You guys got all that? Okay. Nice. I like your drawing. All right, let me stop the share because this is starting to irk me. Last 2 points, just to kind of end on a cool note rather than a sort of boring math note. A couple of ways you can get an iPhone app, like modern astronomy apps like the night sky will tell you when the ISS is flying overhead. Oh, sorry. So I have an app called Night Sky, and every day it'll be like, oh, ISS flyover in 10 minutes. And you can go outside and look for it. That's an easy way to do it. Another way is you can go onto the internet, of course, to get a more elaborate look. Let's just type in, where is the ISS? So I think it's NASA, European Space Agency, has a real-time tracker of the ISS, and it will show you a map of where to find it. What the hell? Oh, here it is. So let's full screen this. So currently, the current position, it looks like it's over Indonesia here. All right. And in the next hour and a half, it's going to be flying over Baja, California, down through Peru, South America, and then it'll come back around to India. So we've got a few laps until we can get it back overhead in Rhode Island. Also, if it passes over during the day, you probably won't see it, right? You got to wait till it passes over at night. It tells you its position in the sky, its speed in kilometers per hour, 27,000 kilometers per hour. That's insane. Another cool thing that I wanted to show you besides this is, as one of the students pointed out in my other class, they have a live feed from the ISS, and it shows you what it's over. Let's see if we can go to that in YouTube. NASA from space camera real-time tracker. I think this is it. Cool. So guys, let me full screen this. Oh. Wait, how can this be live if, is this live? Oh, wow. That's awesome. Look, you can see Earth rotating underneath. You can see, they might be working on part of the shuttle or, yeah. I think it blacks out when it disappears to the other side of Earth or something, but that's pretty wild. You know what's even more beautiful than this is one of the YouTube videos that I really love, and this will be the last thing, and then I'll let you guys go. There's a really cool video called Orbit, A Journey in Real Time Around Earth. And this is in 4K. So guys, if you have like a super nice computer, or if you have like a high-res TV that can go on the internet, I have a projector that displays 4K. And sometimes when I have friends over, if we're having a drink together or something, I'll just put this on in the background just because it's like just cool, creepy shit to have on in the background, and it's beautiful. Creepy maybe isn't the best word, beautiful is. And it's just, you sort of sit there and you just watch Earth rotate underneath you. And it is so beautiful to see it in 4K. Like that, just looking at how beautiful planet Earth is, just to imagine being able to fly that high above Earth and watch it rotate underneath you. You know, they say that astronauts who visit the ISS and look down at Earth undergo a profound psychological transformation known as the overview effect, where you get this different picture of humanity. They say that you don't see the boundaries or territories between countries anymore, and you start to realize, man, we're a bunch of collective organisms living on this little fragile marble, and it makes you want to like get into some, you know, world peace stuff where you're thinking about how people have to band together to solve problems. You have to read the astronaut's description of it. If I talk about it, it's going to sound cheesy, but they were clearly moved by this experience, and it made them feel like they had a profoundly different view of humanity, as in, we're all in it together, kid. We're all floating on this same little marble in space. Another thing that I think is beautiful too is when you look down at Earth, you don't have enough resolution to actually see man-made structures like buildings. You can see mountains and you can see rivers. And by the way, a fun game to play with your friend is to try to guess what landmass you're over. Like it looks like, based on all this brown, that we might be over the Middle East right now, but I'm not sure. I haven't seen this video before, so I'm not sure what part of the Earth we're over. If you guys are better at this, you can enlighten me. But what's really cool is when it goes into the nighttime. Eventually, of course, it rotates into the nighttime side. Let's see if we can find this. Oh, here I was just going over Russia. One of the ways, the book asked this very cool question: how would you know that there were any people or intelligent civilization living on Earth if you cannot see any buildings or structures because you're so far above the planet? When you rotate into the nighttime side of the planet, suddenly the planet seems electrified, and you realize that human beings are kind of like this cyborg tick virus that's spreading electricity and lights across the surface of the globe. And that's one of the key ways you could tell if there was an intelligent civilization on a planet. If you look at the nighttime side and you see these glowing lights, those are viewable from space, and they're actually quite beautiful. So I would encourage you guys sometime to just, you know, if you're just like chilling, reading a book, or if you're meditating or whatever, put this on in the background. It's something that's just kind of cool to watch. And look how great that is, for instance. That just looks so.
Do you have an Oculus?
No, but
there's a live feed that rover on Oculus Quest right now with NASA.
No kidding.
It ends in an hour.
And it's on the Perseverance mission?
Yeah, it's see Mars like never before, NASA's Perseverance rover, and it ends in an hour.
Damn it. I wish I had not. So you can actually like see it in 3D and wear your Oculus Rift like you're standing on the surface of Mars? I need to get one of those. Do any of you guys have an Oculus? Any hardcore gamers out there? I know you're out there because. Wow. Okay. So did you just find that in the NASA website?
I was going to tell you to get the VR headset because they're like $300 right now.
Oh my God.
But,
guys, they released the video, I think. Is this going to be what I think it is? Holy shit. This is the video of the Perseverance. This just came out today. Oh my God. There's the parachute. And you could actually see this rover land. Oh, this is wild. This is totally wild. I don't want to like take up. Look at that. Look at that. That's real footage from last Thursday of the rover landing on the planet. It's traveling through the atmosphere. Whoa. What? This is insane. I'm going to have to watch this whole thing. Look at that. This must be the rocket trying to find the landing site at Jezero Crater. Oh my God. I'm going to send this to all of my friends after I end this class with you guys today. Look at that. This is the thing. Let's see if we can, let's just fast forward to where the crane drops it. I bet that I was talking to the class before I started the recording about this lander. So if you were here for that, you might have heard me waxing about it. Look at that. So this is the rocket trying to figure out where to deploy the rover onto the surface. I wish it gave us information about the altitude. Some of you asked me about that at the beginning of class. Look at this. This is wild. This is so, the last rovers had nothing like this. Let's see if we can get to the end where it deposits the thing. Holy shit, this is nuts. What? Oh man, look, here it is descending from the crane. These must be a couple of different angles. And this was all done completely autonomously. Like it was programmed to do this. There was no one with their hand on the joystick. Holy shit. Wow. That's bonkers. I'm going to have to watch that again. Anyways, I wanted to share that with you guys. Check that out. That's some cool stuff that's happened. I don't even understand. All right, I know I'm like a space nerd, right, guys? I don't even understand how you could be a human being and not think that was cool. If I ever met someone who was like, rovers on Mars kind of sucks, I'm not interested, I'd be like, get out of here, dog. I don't want to talk to you. All right, well, you've wasted another couple of hours hanging out with me and learning about space. It was fun. Don't forget to submit your lab. Don't mess around on Wednesday. Wednesday's class is important. You got the Oculus, John? Damn you. All right, I want to hear a report on Wednesday about, well, sometimes you're not there Wednesday, but I want to hear about how awesome this was, okay? John is about to go explore the surface of Mars, that lucky bastard. All right, I'm gonna have to get an Oculus Rift now. I'll see you guys on Wednesday, okay?
See you Wednesday.
Peace out.